administrative things. This is so let me have a let's think about where we are in terms of this lecture, and what we've done so far is effectively we've done all the documents, we've done the math, we started with the diagrams on Saturday, pretty much went dived into how SVGs work, particular vector graphics and particular SVG. I had a bit of a discussion on tactile and audio tactile diagrams, and today we're thinking about how can we voice some of that, how can we sonify things, and in particular, how do we get information into the diagrams and expose it to the user, i.e. semantics again. And so that's going to be what we're going to do today. Right, so we've already discussed audio tactile graphics last week, and I said on Saturday, I said I'll try to dig up an example. Unfortunately, all the examples I could find from View Plus, they didn't work. I'll show you one, and you can see why it doesn't work. For some reason, it's all screwed up. So let's not dwell on that. So the idea of audio tactile in many ways is extending on the tactile graphics as we've seen them on Saturday, and I'll show you again through the. I'm not sure whether you can see those, but let me stop sharing the screen for a second. So I'll show you a tactile graphic on camera, which I'm not. So you can probably not see very much, but there's embossed lines on the graphic, and I can feel them here. Yeah. And the idea of an audio tactile is now if it's connected to the right device, that it picks up where you are and you touch things on here, and then it tells you what this particular line is. So this here would be a circle, and it would tell you, well, this is a set with 3 elements, and so on and so forth. And then what these lines are, and while you touch them, you get the audio feedback as well. So you kind of can explore things tactily, and then get the feedback in order to listen to what you've actually touched, which obviously gives you a lot more information, or can give you a lot more information than anything you can just put on these graphics as braille labels. So that should conclude tactile graphics, and what we really want to work on today is how about screen reading? Can we get any of these information into some way of screen reading graphics? And there the main idea is, again, well, if you have the information about the components of the graphics, let's embed them in some way, let's give those graphics some proper semantics, and then expose it in various ways. And there's a number of ways how to do this. So if we have information, we can put it in there, and with SVG elements, we've got these the possibility. Sorry, I should share my screen again. I realize I've stopped sharing. That's the one, right? So once we've embedded information into the graphics, how can we do that? Well, first of all, as we've seen last Saturday, SVGs allow us to embed information via title elements, description elements, as well as separate structures via different namespaces. And that allows us to group particular element. So the way we embed semantics is by grouping elements that belong together, giving them titles and descriptions, and possibly provide some sort of a meaningful way of stepping through the graphics by providing navigation options. And the navigation options are very similar to what we've seen for the mathematics. There's a bit more to it because these are SVGs. That means, or definitely SVGs, not just HTML structures. So there's various ways how to order elements. And in many ways, you can think about drawing. If you draw elements, you draw one on top of the other, right? So say you draw a line, and then on top you draw a rectangle, and so on and so forth. And the way you order these already can give you a particular navigation through or meaningful way how to step through a graphic. And so we're going to look at some of these examples now and how to achieve that. So the first one will be Z-axis or Z-axis navigation, which effectively depends on the ordering of the elements in the graphic. The other one would be, again, something like a tapping navigation. And finally, we look at how can we embed a full shadow DOM and navigate that properly. So here's an example with an SVG with navigation, with information. That is taken from height charts. And the idea there is that you can step through the elements. And let me switch on the screen reader. Oh, sorry, I'm in the wrong browser. Hold on, let me fire up a Chrome so I have a screen reader available. Let's go to this. Let's switch a screen reader on.
Document accessibility tab.
And
generic container. 6. Internal link.
Right, so you can hear the screen reader, hopefully.
Window population of the Nordic countries tab. Population of the Nordic countries. Alert. Zoom 175%. Alert. Zoom 175%. Alert. Zoom 175%. Alert.
Hello.
Zoom 175%.
I'm sorry, I don't know what the screen reader is doing right now, but it's not what should happen there.
Alert. Window document accessible. Alert.
Well, clearly that doesn't work as expected.
175%. 2. 1. Window tab. Population of Nordic countries.
Well, it should speak, and it doesn't. For those of you who can see the screen, you can see that the tap information, the tapping works, but for some reason it doesn't speak. And I'm not quite sure why. It should. It does it, well, maybe it does it here.
Pie chart. Population of Nordic countries. Link 1.
Nope.
Internal link. Population of Nordic countries. Link.
Well, sorry, it doesn't want to speak for me. Let's have a look at another example. Maybe the others work better, hopefully. So the others are not from height charts. So the others are. So I've got a couple of examples where I've used some of the chemical diagrams that we built and just embedded information as title and description elements, and then just had a regular tab order of 0 on there. And let's see whether that works.
Breadth first. Link. Aspirin.
Yeah.
Consisting of ring with 6 elements and functional group COCOCH3 and functional group COOH.
Let's zoom a bit.
Zoom 125%.
Right.
Benzene ring substitutions of positions 1 and 2. Functional group ester. Functional group carboxylic acid. Carbon 1.
So we can. So what all I'm doing is pressing tab all the time, and so there's the tab order. So they all have a tab index, all the elements in there, and they all have tab order 0, and we can just step through them one by one.
Single bond. Carbon 2. Double bond. Carbon. Single bond. Carbon 4. Double bond.
You can't really go back, but yeah, you can just move through.
Oxygen 2. Single bond.
It's fairly tedious to move through all the elements. So let's not do that. Let's have a quick look at how the actual code looks like, so we understand what the order is in which we actually traverse the tree.
Window view source localhost 8080 resources SVGS aspirin noted VF HTML tab.
So the way you can shut up, Chromebox.
8080/resources
Doesn't stop.
/aspirin noted VF HTML.
Sorry. So what you can see here is so all the elements are ordered, right? And the way they are ordered means that that's the way we just step through them. So they all have a tab index of 0, as you can see here. And they are all ordered in a breadth first order, which means that we step through the tree by, you know, if you think about this tree as a tree with the top element is the SVG, as that title amount, then it has 3 children, 3 groups. 3 of these are different types of sets. One was the ring, one was the functional group, and the second one is also a functional group. And then after that, we step through all the children of these sub-elements, right? Just to go back and show you how that worked here.
Molecule consisting of ring with 6 elements.
Right, so the ring with 6 elements, we step in there.
Benzene ring substitutions at positions 1 and 2.
So it's a benzene ring, so that's the first big structure. Then we step the next one. And the next big structure. Functional group carboxylic acid. Next big structure, and then we kind of we've done the first row of the tree. Now we step one further down, meaning that we now start on the first node, which was the ring, all the elements underneath there, which are the components of the ring.
Carbon 1, single bond, carbon 2.
Right, and step through those, and so on and so forth.
Population of the Nordic countries.
We don't want to see that. Sorry, I don't know where my slides are. Here they are. Right, let's have a look at the same graphics, but using a depth-first exploration strategy. Again, this is only being built. This is only being built using the arrangement of the graphical elements in the actual SVG.
Aspirin, molecule consisting of ring with 6.
So that's the aspirin again, right? So the aspirin has the ring and these 2 functional groups, and let's get into that first.
Benzene ring substitutions at positions 1 and 2.
So we see the benzene ring first, and now in the next step,
carbon 1.
We now dive into that ring first before we move on to the other structures. Let's quickly walk through that bit.
Single, carb, double, carb, double bond, carb, single, carbon, double bond.
Now we are at the end of the ring. Now we step into the next major structure.
Functional group ester.
Right, so we effectively go one layer of information back up and now step back down again. And then we can walk through this. Right? And just to see how that actually works in terms of the code.
Window view source localhost 8080 resources SVG S aspirin NotaGF HTML tab.
And unfortunately, the screen reader doesn't like to be stopped. The screen reader doesn't like to be stopped if you're on source view, so it just doesn't react because it doesn't recognize it as an HTML page. Anyway, now it's done. Let's have a look at the actual code there. So the way that the elements are now arranged visually determines how they're being stepped through, and the way that it's being done is by simply having effectively the topmost element. Of course, topmost element is again the SVG with its title, but then underneath there we have the first atom set, which was this ring structure, right? So that's this first group, and then we immediately draw all the single atoms for that. So kind of arrange it depth first, and after that, only after that, we draw the next set, and then draw underneath there all the elements of that set. So the way things are being drawn, the order in which they're being drawn now determines how we step through that. Now,
so Volker, so does it mean you cannot really choose between the two? The way you have coded will be carried through in terms of tabbing.
Exactly, yes. So the way this is ordered will determine how things are being done. So you can't really do anything. Once it's in the page, once it's drawn, that determines the order. Right, and obviously, and that is just from the drawing order. We can do a similar thing just using the tab order, and let's do that here.
consisting of ring with 6 elements and benzene ring substitutions.
Right, and that's the benzene ring again.
Carbon 1.
And we do the same, and it is a depth first traversal again, but this time we have a quick look at the code.
Window view source localhost 8.
And just ignore whatever Chromebox tells us. But here, just to show you the difference between this particular one and the previous source, now we see again, this is the breadth first ordering in a way. So the breadth first ordering here gives us now the 3 major groups on top. However, we've reordered it by using the tab indices. For those of you who can see the screen, now we have a tab index 1 and we have a tab index 2, and the tab index 2 is actually somewhere else than the next drawn element. So we effectively jump over one of the drawn elements before we then go back, and then the next major drawn element then would be a tab index 14. So in many ways, that's the idea again of putting order or information on the navigation into the diagram using tab orders. And that's slightly more flexible, but it's still not that flexible, because now what we have is we have the visual order, which we could exploit, and we have the tab order that we artificially add. And neither is ideal, of course, because what we really want is something that we'll now do here in this particular example, and that gives us now full flexibility. Well, let's have a look at that. So this is the same aspirin molecule. Oops. Now it stopped talking to me. Why? Right. Now it's talking again. Thank you, Chromebox. Let's try that again.
Navigatable diagram. Application.
So it tells me it's a navigatable diagram. It's an application. It sits there on the page, and I can now press A and start the animation, if you like.
Aspirin.
So now I walk into there, and it tells me this is aspirin. I can instead of just telling me everything at once, I can ask it for more information.
Consisting of ring with 6 elements and functional group COCOCH3 and functional group COOH.
All right, so I can get more information out of that element if I like. I can do other things with it. I can change the background. Let's give it a bit more, a bit higher contrast in the background, because I'm aware not everybody can see black and white in these slides. And then we have a more flexible way of navigating this. So I'm now using the arrow keys.
Benzene ring substitutions at positions 1 and 2.
So I have now walked again into the benzene ring, because that's chemically the most exciting structure. That's first. But I now have a choice. I can either walk right and go effectively to the next major element in the drawing, or alternatively, let me go back to the ring. I'm back on the ring. I can now, using downward arrows, I can now actually go down.
Shared atom carbon 1 with functional group ester. Double bonded to carbon 6. Single bonded to carbon 2. Single bonded to functional group ester.
And it gives me an additional information on what this atom is, and I can now start walking around the ring as before.
Carbon 4 bonded to 1 hydrogen.
We don't have to listen to all of it, but in many ways I can now go back up as whenever I like. So and I can of course walk across to the next group, and I can walk down there, and so on and so forth. So in many ways I have a much more flexible way of exploring this structure now than I had before. And I'll show you how that's being done. And this is being done with what's called a shadow DOM, or what's kind of it's an additional structure that I embed either straight into the SVG or into the page, depending on how things are being loaded. And let me switch off Chromebox for this part, because otherwise it'll get really annoying. Right, and the way this looks like is, oh, we can't really see anything I'm sorry, you can't really see anything in the code, but what we can see is when we actually have a look at what an element is sitting in the page, you can see here the element sitting in the pages. That's once the SVG, which just sits in there, and it doesn't matter how it's being drawn, right? This is now absolutely arbitrary how it's being drawn, what the drawing order of the elements is, because we do not no longer use tab indices. Instead, what we use is a shadow DOM element, which is effectively a separate XML structure on which we do the navigation, and which contains all that information about what these things are, how they're being linked to each other. So we are no longer bound to the pure tree structure. We can now walk around and walk along the elements as we like, because we now have the information of what are the neighboring elements, what are the parent elements, what are the children, and so on and so forth, in a separate structure, if you like. And you can see, for those of you who can see, there's various types of speech elements, and they're not even filled in. They're pointing to message elements, and these message elements are given somewhere else. And what that allows you to do is, and I'll show that. Let's switch on the screen reader again for a second.
Document accessibility tab. Navigatable diagram. Carbon 1. Navigatable functional group carboxylic acid.
Right. So what this allows you to do is change languages on the fly. Let's change a language. That doesn't speak. So this is Japanese. That if I were to switch on a Japanese voice, it would speak. What else do we have?
Functional grumpy carboxyl.
That is German. And that obviously is horribly mispronounced by an English voice. But you. Now we're back into English. Oops. But just to show you that in many ways you can now embed as much information, as much semantics as you like into your graphic, and exploit that in a far more flexible way than just by having tab orders and drawing and effectively leaving things up to the browser and the screen reader alone, and how things are being done. Right. So in other words, what we've done with our little graphic here is we've really turned it into a kind of rich web application on its own. So you have all, you can change the colors, you can do all kinds of trickery, and as the way things are being pronounced, the languages we're using, and so on and so forth, all on that single graphic alone. Right. Let me switch off Chromebox again. Right. Right, so now the main question is, of course, where do we actually get all this semantics from? Where does that information come from? Well, obviously, the easiest way to get information into a graphic is using some manual input, but that's also the hardest way to actually get any information in there. Second one is using just some standard image analysis, and then finally, we can think about computing it from scratch with image analysis, knowledge and knowledge system in the background, as well as potentially using just models and certain representations formats that are available to us from different systems. And so what about providing alternative formats for diagrams when we don't know what things are, right? When we don't have any information? Well, as I said, we can provide alternative text, which is generally not enough, but often good enough. And that can be augmented with captions. How do we get these captions? Well, one way is to do things automatically, and let's see what right. So here's, for instance, here's the caption bot pod from Azure, from Microsoft. Let's have a quick look at, I think I've prepared some things here. If I can find my right slide here. Is that the one? Nope. Captions, there you go. Right, so Caption Bot is provided by Microsoft. It's free of charge. You can just upload any image. We're uploading a couple of cats here now, and see what it comes up with a caption, right? So what it does now is uploading the image. It says analyzing image, and it comes back. All right, and what it says is, oh, I think it's a couple of cats sitting on a wooden surface or wood surface, which is pretty accurate. So that's exactly what's in the picture, right? Cats and dogs is always easy to recognize for some reason, and yeah, that's probably all we ever need in order to describe that picture. There's not much more you might want to put into a caption for a picture like that. Maybe the race of the cats, or maybe what type of wood that is, but really it's not all that exciting. Because what is interesting about the picture, although it's fairly rich in the case of having different colors and different elements and so on, it's fairly information free. There's not much information that you have to really gain from that image. Let's try something which is in many ways a lot simpler. Let's try this one here, which in many ways is a lot simpler and a lot graphically a lot easier to see. And it's a parabola, and the parabola is x squared, obviously, and it's on a coordinate system. And what does ASUA tell us? Well, it says, I think it's a chart, maybe, or line chart. Yeah, not even close, I would say. Not even close. Yes, something chart-like is there with the coordinate system, but it's definitely not a line chart. It is a graph. But, you know, it's as good as it gets, if you like. But it's certainly not anything you want to have as a caption for this. Let's put something else there. Let's put a box plot there. For instance, this. Maybe it does something with that. Ooh, that's already. It's much better for this one. For instance, I think it's a chart. Yes?
I think Neha has some question.
Oh, right. Sorry, I haven't been paying attention. Let me finish my sentence and then I'll get to you. So it says it's a chart, a box and whisker chart, which is already pretty good. But unfortunately, probably not enough in terms of information you want to learn from this particular chart. Yes, Neha, sorry. Go on.
Yeah, okay. So when the end user is exploring this SVG diagram, so if we assume that he or she is cannot see the image, so while exploring, will they know where they are on that diagram, on the left hand side of the diagram or on the bottom part?
No, they don't, and they don't know where they are. And I'll talk a bit about that in a minute. And they don't need to know. That's the interesting thing. Okay. Let me go through those diagrams for a bit. And then I'll show you a much more exciting one than the one we've just seen, the aspirin one.
Okay. Thank you.
So these diagrams here, right? Why is it not great what ASUA does for us? Although it's already pretty good. Let's face it, you know, recognizing that this is a box and whisker chart, certainly better than what it did on the parabola. It is not very useful because what you need in STEM is really more precise information, right? And therefore we need to get that precise information. We have to get it from somewhere, and then we have to get it into the graphics. And where can we get that from? Well, sorry. First of all, the one way you can get it is straight out of models. So if you have a model already, if you have the right kind of data and you can export that, that's already nearly everything you need. And then you can try to expose that. So again, here's a graphic which is done in a similar style to that molecule I've showed you earlier, where you can just start looking at the element. And let me again switch on the screen reader. So you get the benefit. So let's start this.
5 box plots for ozone. Title box plots for ozone. X-axis plants. Y-axis ozone. 5 box plots vertically. Box plot for 5 and quartiles in 1, 11, 18, 32, 45 and 1 outlier.
And now you can navigate this in a very similar structure way. You can navigate it forward, and you can navigate and you can dive deeper, and so on and so forth. And if you can't see the screen, it's also being highlighted and magnified and so on and so forth. But the information that's in there is so so much better. And it comes straight out of the model that you can compute inside a system called R, that's a statistics system, and which allows you to export that straight into these SVGs. And to answer Neha's question, which is effectively the next example I show you, and that is an example where the semantics is not, well, can be computed out of chemical knowledge if you have that for a chemical diagram. If you have a chemical drawing system, for instance, it has a lot of that information that you want to put into these elements already in the chemical drawing, and therefore can be exported in chemical file formats. If you don't have that, you can again go through image analysis, but you have to do a bit more image analysis than just a statistical lookup of what things are. That's pretty much what Azure does. That's pretty much what companies like Facebook do and Google and so on. They just have massive databases, or not databases, but data and information that they can exploit in order to do a statistically based image analysis and recognition of elements. What you need for STEM is you don't just want to know that there's a bunch of cats in the picture. You actually need to know what cats they are, how many eyes they have, and so on and so forth. In our case, what is the chemical structure? It's not enough to know this is a molecule. It's important to know what kind of molecule it is, because it does make a difference if you're a doctor saying you prescribe somebody aspirin, or if you prescribe them heroin, right? That can be, considerably a problem if you're not precise enough. So precision is important in our subject areas. And therefore, instead of just doing simple image analysis, what you have to do is explicit recognition with a knowledge-based system that allows you to recognize these graph structures. And I've put a graphical representation of a molecule into the page here. Which is actually from a US patent database, and that is being recognized automatically by a piece of software that then tries to identify the rich structures, so the big structures in the molecule, and name all of these automatically using web services. And what you then get is, again, a navigatable diagram, and in that case, and this is interesting and leads us to Neha's question in many ways. If you start navigating that, and change the color a bit, let's zoom in a bit. Let's zoom in. 110. Thank you. And now, what is the first one? What is the first element we would now navigate to? Now, the way this is being determined is by the software by chemical importance, meaning that what is a chemist that would look at this, what would they deem the most important part of that particular structure? And interestingly enough, it's not anything visually here on the left-hand side, it's something visually on the rightmost side. Now, if I continue navigating this molecule, I want to go to the next one. The navigation now, next means you press the right arrow key.
The pyridine ring substitutions at positions 1 and 4.
Now, you notice that although I pressed the right arrow key, we actually walked visually left in the structure. Now, why is that the case? Well, there's a couple of reasons for it. One reason is that, as I said before, why do we walk to this structure next? Because that's chemically the right order in which to walk through that element. Now, since it's to the left, why don't I have to use the left arrow key? Well, that goes back to tests and experiments we've did with navigation models. And it turns out that, if you give a blind kid this molecule and you ask them to navigate it, they don't really care about whether that element is to the left visually, because they don't see it anyway. They want to have a consistent navigation experience, regardless of where that element is being drawn on the page. And so the interesting thing, for instance, in these experiments was when we gave it to the blind students, they perfectly managed to walk through these elements. Whereas their sighted teachers often were struggling because they were trying to walk left and hitting the left button, and it didn't go anywhere. Because if I'm at the beginning of this and I hit the left button, I don't get anything. I don't get anywhere. I'm just stuck, right? So then the next question is, of course, well, why don't we arrange it in the drawing so that it actually, the important stuff is always on the left? Well, first of all, that's not always possible. Secondly, it's not always desirable either, because the way these are drawn often is important for the authors that draw these elements, as well as chemically relevant, because sometimes the arrangement of these substructures really mean something, and therefore you do not want to mess with that. So the layout algorithms, they can draw things differently, of course, but one thing you don't want to mess about is the way authors intend these diagrams to be seen and read. Right.
Volker, does it mean that visually, the same arrow, the left arrow could mean going right or left depending on what order it has been put in? Okay.
So effectively now my navigation model, so I go down, of course, right? And now on my navigation model, I go to the next element on the same layer. That means I go to the right. Think about it as a tree. And the tree, the leftmost side, the leftmost node in the tree, and then you walk along that same level of the tree, and you walk kind of right. And visually, of course, you walk left in that particular example. As I said, for those who don't really see the screen, it doesn't matter. For those who can see the screen, it is a bit unusual, but our user experiments showed that it's more important to have a consistent navigation model than one that actually corresponds to what you have visually. We've also experimented with another one, which was a kind of a windrows model, where we used the entire keypad, or the numpad from 1 through 9, to have kind of north, south, east, northwest, north, south. North, south doesn't exist, right? Northeast, northwest, and so on navigation, like in a windrows. In order to model where you are visually, or kind of to sync up the navigation with the visual on the screen. And it turned out that really didn't go down well, because people were just getting very confused. First of all, because they had too many options to navigate in. Secondly, they didn't really know which direction they had to navigate into. And also, it's not necessarily easy to map what you have in the image onto such a model and say, okay, well, northeast-ish is this particular neighboring element, and southeast is this one. That didn't go down well. Let's put it this way.
But so, it will become very much depending upon the domain, because let's say graph structures, you may like to, very often it will be like left to right, because you have an x-axis which gives some idea of either time or either some parameter and you want to see that. Maps,
that is true.
And the maps, for example, you perhaps also want actual direction to be linked, whether it is to the east or to the west. But let's say if you're talking of geography type of geographical maps, so it will be very contextual.
Yes, but again, one of the problems there is that if you don't really see, whether something is downwards or left or right, it's the consistency of the model or of the navigation is more important than actually the correspondence to the visual, right? So yes, so I agree that if you know that you want to go north, that kind of going upward and downward for south makes sense. But say if that graphic then still is kind of spun around and doesn't have north, west, south as you would expect them, the north to the top and south to the bottom, then still you want to map it to a model where if you go down, you go south, no matter whether it's visually upwards or to the right. So this is, I think, the takeaway message from that. And the things we've experimented with were primarily things with statistical diagrams, as well as circuit diagrams, where you have a lot of circuitry. So where it's more important to walk inwards and outwards, which is better modeled with up and down than with anything else we found.
But one ambiguity I can see in this, if your textual descriptions actually talk about right left, then there could be a problem in this type of a navigation. If the supporting textual description in the textbook really says that this benzene ring is to the left, now there is some idea the user need to have, the reader need to have of the position. If the textual
I agree. I agree there, but that is then just a problem of using the wrong description, right?
Yes.
No, or using not the wrong description. That's wrong. Using a not or not comprehensive enough description. You remember the diagrams we did in one of the first lectures, where we're discussing the captions which were referring to colors in the diagram.
Yes. Yeah.
And which we then improved because the colors could change due to changing the color palette with a high contrast and all these things, and or going to black and white, and then the colors were meaningless. Where we then improved upon these captions by saying, oh well, you know, this is a dashed line and so on and so forth, and this is the first line. And you have to use a similar techniques for these diagrams then as well, right? Because, you know, but because if you tell, yeah, it's to the left and it doesn't really correspond to your navigation model, you can then say, oh, well, this bit is kind of the second most important element, which is drawn on the left, or something of that nature. Anyway, sorry, I saw Akash, you were also putting a hand up.
No, well, actually, my doubt is clear now.
Oh, okay, good. All right, so we've taken care of that. Let me see what else I wanted to talk to you about. Oh God, too many things. I think I've got too much. That's the thing. We'll take a little break now, and then we start with sonification right away. I'll leave you with one of the things that we can do with these diagrams. I've already showed it to some of you at the end of the last lecture or after the last lecture. Although you can see it, if you can't, this is a 3D printed molecule, similar to one of the ones we've seen there. It's not just 3D printed. It has braille labels 3D printed, not embossed, 3D printed on it, and pretty much it comes out as an SVG, but obviously it's a lot more information rich than anything we have here on the page. Right, let's take a little break, 3 minutes, and then we'll discuss sonification.